Hello, everyone. I'm so glad you're here today to listen to my talk about broken promises. And it's something that I feel very passionate about. It's something that I'm actually excited to talk to you about today. I'm from Lightbend Company. I don't know, you may have heard of us. We were previously called TypeSafe, the stewards of Scala, Akka, and other frameworks. So I have some good experience with the enterprise and dealing with the dangers of data. So I want to start by saying data is dangerous. And I can say that because I myself have been hurt by this. I've witnessed hurt in other in systems that have been built. I specialize in building high-scale, high-throughput, large systems for enterprises. And as in any company in the enterprise, you can see wild things. You can see things go crazy. Data does a lot of stuff. It lies, it cheats, steals, kills. Maybe not kill. I mean, we hope it doesn't kill, but it does a lot of bad things. And when you're building microservices or doing distributed computing or building distributed services, you're really required to cooperate in order to achieve an end goal. You can't achieve certain ends without being able to cooperate. And in order to cooperate, services need to be able to trust each other. They need to be able to trust that what they see is true, the data they're working with is true, the data they're working with is going to inform them well. And microservices should also be cooperative, but not parasitic. They should be symbiotic, meaning if I'm hurt, that doesn't mean that I should hurt someone else. If someone hurts me, it doesn't mean I should ripple it through for other people. And so microservices have this relationship with each other, but they also have a unique relationship with data itself. They relate to each other, but they also relate to data. And they relate to data in a couple of different ways. There are a few different types of data that services need to work with in order to achieve their goals, in order to cooperate in the best ways. One is your agent data, the data internal to your microservices and internal to the agents or components or entities, sometimes we call them, within your service. You also have persistent data. You have data that's persisted regarding those entities, perhaps. You have data that's persisted for other reasons, but there's persistent data in your system. And you also have external data. So you deal with the data coming into your service from perhaps other services or perhaps consumers or users. But in the end, you have some external data that you must manage. And I'm going to talk about what that data sometimes does and how it can destroy the relationships that you have. One thing that data can do is data can lie. Data has lies of omission sometimes, meaning that perhaps it gives you a partial view of what you need in order to tell the truth, in order to achieve a goal. For example, say you had an address and that address was entered without the full information needed in order to ship somewhere. That means that address was created with missing data. Your data was created incomplete. So it was a lie of omission. And then sometimes you could have lies of commission, meaning that the address was complete, it was full data, but the data was wrong. Perhaps you gave the wrong address or the wrong zip code or the wrong something or another. That means, again, you can't fulfill what you were supposed to do, as in shipping something to a person. So you have this created wrong data, which is a lie of commission. Data can also be corrupt. Data can be corrupted by good or bad actors. It can be corrupted intentionally or unintentionally. If it's not protected, if it's not isolated, it can be incorrectly modified. It could have race conditions, and data can be very susceptible to this corruption. Data can also be very high maintenance. And who likes a high maintenance relationship? Hey? Nah. Data can be hard to secure. And if data is only hard to secure in a specific area, but everyone has to pay the burden for the difficulty to secure that data, then it's kind of high maintenance. And you don't really need that burden. For example, so you have some data that needs to be PCI, PII, SOX, BANES, everything like that. And it's just a small component or a specific component of data. But say it lives in a place where everybody has to fall under that same security just because that data lives in the same space. I mean, it's a burden unnecessary for others. So it's pretty high maintenance. And the really important thing that you'll find out here is that data itself is dumb. Data is dumb. It is not self-aware. It is very hard to have a trusting, healthy relationship with something that is not self-aware. Data, the funny thing is, data doesn't even know when it's wrong. It doesn't have any logic to know it's wrong. It's just wrong, and you're crying, oh, but you're wrong, you did this, and it's like, but I'm here, and this is what you've got. And it has no idea how to correct itself. It doesn't know how to repair if it's corrupted. It doesn't know how to say sorry if it's lied. It doesn't know how to apologize. I mean, data can't do any of that for you in and of itself. It's simply there. And it's interesting because we had this really great buzzword for a while in enterprise architecture, which was we're having data-driven systems. Our systems are going to be data-driven, and that's going to fix everything because it's data-driven. But I think it's dangerous. I think that calling something data-driven is a little bit of a recipe for disaster because something that is not aware, something that is purely just dumb, cannot really drive anything. Data is too dumb to drive stuff. In order to drive something, you need to know direction, you need to be able to steer, you need to be able to interpret, you need to have some logic, and let's pretend that we're not talking about stored procedures here who may have tried to do that. But in general, data is really just there. It is what it is. And you have to have agents who can act on that data. You have to have things that can be informed by that data. And that's really what the purpose of your data at its core is. Your data is there to inform. Data-driven architectures made a promise that it could not deliver on. And you can see that as we talk about why data is used to inform, how it's used to inform, and how you really can become to trust it. So maybe a better way to say it would be a data-informed architecture, or maybe something totally different. But to call something data-driven is sort of, in my opinion, a little bit dangerous. Another thing that I find dangerous is this idea that everything will be a stateless architecture. And I'm not on one extreme or the other, so I'm not here to say stateless is wrong, never do stateless. But what I will say is that stateless architecture, if taken only, and I'm doing stateless across everything for any reason, it can be another broken promise. Why? Well, I mean, if you say you have a stateless architecture, the truth is what you've really done is moved your state that you do need to maintain. You've just pushed it down another layer or off to the side. And what's interesting is you've pushed it into the dumb layer. So you've pushed the state that does need to be maintained, the state that is required in order for you to deliver on what you need to deliver. You've pushed it to the dumb part, which can't do anything about itself. It can't correct, it can't fix conflicts, it can't apologize, it can lie. I mean, it's not a very safe place to put your state. So if your services can't rely on data, if it can't rely on it to properly inform, then what do you have? If I can't trust the data to inform myself, if I don't trust the data to inform others, or maybe I trust the data to inform someone else, but I give them bad advice, then I hurt my reputation. Perhaps my service gets knocked down a couple of levels. Perhaps I have some degradation notes. Someone puts a ding on me. Oh, I got the wrong answer from that person. The score is lower. And you want to be able to trust it. So you need to be able to actually design trust in your systems. You need to be able to design systems that are at the core trustworthy. And it's easy to say, but it's not necessarily always easy to do. Because you need to be able to make promises. If I have a microservice, if I have a system, and I need people to trust me, that means that I need to be able to make promises and keep them. A promise is not necessarily a guarantee. I'm not saying that you make a promise, that's the same as a guarantee. Whatever happens, it will happen. No, it means that you at least have an intent. And for any reason, it may or may not happen, but you have an intent. And to be, I guess, more scientific about it, as Mark Burgess says, who's the creator of promise theory, in order for you to have guarantees in anything in the world, you would need irresistible force and unlimited speed, I believe is what he calls it. And I don't think there's anything that we found yet that has that. So whoever's telling you that there are such things as guarantees is, kind of some lying data there. But promise theory itself is an engineering framework. And this engineering framework is meant specifically for coping with uncertainty in information systems. Promise theory is not about a language construct. We're not talking about play promises or promises with futures or something like that. I'm talking about this theory, this mindset, this form of design that you would use for coping with uncertainty. And the real operative phrase being uncertainty, coping with uncertainty here. And the more you can cope with uncertainty, the better you become at being trustworthy and resilient. And the way we do this, one of the ways that we talk about coping with uncertainty is being able to use promises to do that. And being able to do that really increases the trust that you have inside of your system. So, what is uncertainty? When we look at uncertainty, when we think about uncertainty in our systems, I'm sure you can think of a number of things. But one of the things that I like to talk about or try to drill down as an example is looking at divergence versus convergence. What does it look like for data to diverge or state to diverge or state to actually converge? When we talk about divergence, we talk about going from a known state to an unknown state. And this is not something that you want to do. You don't want to start with a known state and go into an unknown state. So, for example, if I'm in a car and I get pulled over and there are 4 people in the car, there's myself and 3 other people in the car, and the cops say, "Hey, what happened? Do you know why you guys got pulled over?" Something like that. I mean, does it make sense for all of us to start talking at once? Or should we all start talking at once? No matter what happens, if we all start talking at once, we're probably going to go from that known state of no one's in trouble into a state of, okay, everybody's in trouble now, right? That's if we don't have collusion. But convergence, on the other hand, is understanding the state of where you're trying to go. And it's being able to make all the necessary pivots. Because if you know where you're trying to go, you're able to make all the necessary pivots in order to get to where you were trying to go. For example, if I have a Rubik's Cube, I know the state that it needs to go to. And I know that I need to make a number of turns and pivots and things to do with the cube in order to get it to its final state. That state itself is an intent, it is a promise. And when you have convergence in that way, it better allows you to parallelize work. You could specialize your work, you could parallelize your work because all the agents, all the actors know the end state of what they're trying to get to. So promises are what really help you to converge. It helps you to go from an unknown state to a known state. Like I said, that completed cube is the known state. But it doesn't try to tell you the starting point. It doesn't try to tell you what to do. It tells you what it wants, what I want, what I promise, what I intend, not how to get there. Sometimes if I think about rules engines, and I know rules engines mean all the best in all their glory, but if you could imagine a rules engine trying to tell someone the steps or trying to help you solve a Rubik's Cube, trying to encode every single thing you could possibly do from every beginning point, from all the unknowns into a Rubik's Cube, it wouldn't work. It wouldn't work. And sometimes that's why I think, rules engines, I'm sure they definitely have their place, but you should really think twice if you're using a rules engine to tell you how to converge to a place which could have a complex state. So why wouldn't we say obligations are better? Could obligations be better than promises? Wouldn't it be better if I told you to do something and you always did it because I told you to do it? It seems like it would be better, but impositions without an agreement are another thing that cause fragility. You cannot impose something on an entity if you don't know if that entity is able to do it. Maybe it will try, and maybe it's not able to. Maybe it doesn't have the data to do what you've asked it to do or try to tell it to do. You have to understand, I cannot throw something at you, for example, and force you to catch it if you're not ready to catch. If I didn't say first catch, you say, oh, because you know you're about to catch it. Because if I do that, then I'm really just throwing something at your head, and it's not right. And I know we tend to think that, we have this idea of rebellion. And we think maybe, rebellion is something only for humans or animals or other things that can make choice. Not for machines yet. Except for when the robot colony comes, then they will rebel. But your systems can rebel too. Your systems have this way of rebelling by failing, by giving you wrong stuff, by falling over. If you try to put some imposition on it for a specific type of performance, it can't deliver. Sometimes it quits. Obligations are not better. Impositions are not better. It's better to understand what's truly available to you, what you can actually use, what has been promised, and be able to deliver on that. So back to how we do that. Back to the data and winning trust. How do we marry this with our promise theory, with trusting and being able to really cooperate with our systems? We started with this premise that data is sometimes destructive. Sometimes it lies. Sometimes it's corruptible. Sometimes it's high maintenance, and a lot of times it can be unintentionally dumb, and it needs help. And one of the ways that we can help the data is to really understand what categories that data fits in. So first, let's try to understand the category of the data, and then we understand how we maintain that data in our architectural framework, and then we look at the tool, a specific tool. There are others that can probably do the same thing that helps you to do this. So we have facts. And facts should be immutable. Facts should be immutable, and sometimes we call facts events. We have events. And I say they're facts because there are things that have happened. This is something that really has happened. And it should be relevant, it should be immutable, it should be germane to the state that we're trying to maintain or to the promise that we're trying to keep. It should be able to be used to assess whether or not a promise has been kept. You need to think about what makes a good event to keep. Every event is not an event to keep, or sometimes you may make events that aren't good events, that aren't good to be reused later. You have to look at what makes a good fact, what makes a fact bad or useless. You have to look at, okay, are truth and facts the same concept? There are a lot of things that you need to be able to determine there as you start designing. So we have our facts on one side, and that's a specific type of data. And then we have another type of data, which I like to call opinions. And those are views. And sometimes we have a hard time determining what's a fact and what's an opinion. But that is something that we really need to be able to do. Views, opinions. They should, most times, be generated by ingesting facts or understanding the facts of your system. Views should generally be based on facts. Sometimes we make views that aren't based on fact. Sometimes, in some parts of the universe, that's okay. But generally, they should be based on facts. Those views, those opinions, could be used to help observers understand whether or not a promise was kept, whether or not an agent did what it was intended to do. And so our system, being composed of both of these, both facts, events, or opinions, or views, are something that need to be maintained or stewarded in two totally different ways. The characteristics that you need to have for facts, or the way you deal with your facts, the way you deal with that, the stewards over those, have a different job than the stewards over your views. Those views are the storyteller. They're the trusted advisor. They're the ones who, I take these facts and I opine about it sometime, and maybe I act on it. I publish a paper. Or maybe if I'm a system, I publish a recommendation. I think this person will like this thing because I've looked at the facts and I've got something to say about it. But these are two totally different views and should be handled in a different way and handled by different parts of your system, different components in the system. So we need to give this data being either facts or views, they need a master. And they, of course, need a benevolent master or steward. We can use them both hand in hand. I always imagine a benevolent master to be a good steward as well. But those masters or stewards should be able to be capable of making and keeping promises in your systems. And you can have stewards that are stateful, as in stewards of your events, or you can have stewards that are stateless, the ones who create your views. So what makes a good steward of state? Good steward of states should be smart. They should have intelligence. They should have knowledge. If I'm stewarding the state, meaning I am in control of the events, the facts that are being created, or the facts that are being used to recover my state, if I'm in charge of taking in commands or requests and understanding whether or not they're valid or they should be used to change my state, et cetera, I need to be smart about it. I need to have some intelligence. I need to be able to produce relevant events that will be helpful not only for my state, for others. And I should be able to know what is a good fact and what is a bad fact. I also need to be able to have boundaries. I need to have clear, properly managed boundaries, which means I need to understand my context. I need to know the context that I'm in, and I need to be designed with a specific context that's only specific to the promise that I need to keep. And sometimes we use in domain-driven design this idea of a bounded context. And you could think of it in this sense, a bounded context that allows you to hold those promises and keep those promises and manage the data in that context itself. I need to know what actions are valid for my state. I need to know all the different contexts I can become within my state. I need to be able to build these promise boundaries. That is what I need to do as a good steward of stateful information. I need to also be sensible about the state. I should not pull in more information than is required in order to achieve the promise that I've promised. I should not overburden with things that are unnecessary. Specialization matters. It's important. And another thing is I should be resistant to corruption. If I'm a good master of state, a good stateful master, I need to be resistant to corruption. That means I need to be able to validate data that comes into me to make sure whether it's come from a bad actor or a good actor that no matter the intent, that it is something that I should deal with or how I should deal with that. I I shouldn't be able to be taken down by some outside service unless I explicitly say that I'm going to subjugate myself to someone else. But generally, I shouldn't be able to be taken down by someone else going down. Another way to be resistant to corruption is I should be idempotent. I should make sure that the logic inside that maintains my state, that helps me to maintain my state, is idempotent in nature. Because one reason that we end up with corrupted data sometimes is because we have a lack of idempotence or some poor stewards. And a good master is also autonomous and responsible. And that autonomy leads to greater certainty because you have control over yourself. You have control over yourself. You can act on everything that you have, all the knowledge that you have. You can only conflict with yourself. And you have all the information necessary to resolve your internal conflicts. Thus, you are independently resilient. So how do you repair yourself as a stateful steward? How do you repair the state that's inside of you? Repair meaning go from a potentially corrupted state to a fixed state. And one way we do this is by rebuilding the state from events or rebuilding from facts. So if I have some state inside of me and somehow it gets corrupted, something happens, I can go back in my time machine and look at the facts over time and rebuild the state, even in the face of potentially catastrophic failures. Another way I can rebuild my state is by compensating actions. If, for example, I have a state of an account and I say I've sent some money and I never get the idea that, finally I get an event back saying that money never arrived or the money wasn't sent or there was an error on this side or such and such and such and such, someone needs to compensate and put that money back. I need to compensate and say, oh, the money actually is still here. It goes back. And also, I need to have the information that I need to execute and resolve those conflicts, any types of conflicts that I may have. And so that's for a stateful actor or agent. But a stateless advisor or view creator or opinion maker, whatever you want to call it, how does that person repair their views? How do you fix your opinions? And one way is you can also rebuild your views from facts as well. So if you yourself are a consumer or a subscriber to the facts being produced by someone else, and those are the facts that you've used in order to create your view, you can use those facts. You can also replay those events to rebuild your views. Earlier I said we should generally base our views on facts. But some views need to be fact-based, and sometimes there are others who don't. But if you have views that need to be fact-based, you should only allow CRUD actions, maybe only read-only CRUD actions. Otherwise, you'd be unable to accurately reconstitute those views if they come from external sources. So everything outside of the fact producing, you should use as read-only. But sometimes you have views that are not fact-based or don't matter, or if it gets blown away, it's so temporary that a new thing comes up and it really doesn't matter. And for that, any CRUD actions, just fine. Doesn't matter what you do, just fine. In any of these situations, you can use ACID. I know sometimes we talk about when we look at state or event sourcing, and I know you kind of hear the keywords here, but I'm not trying to throw out the buzzwords, but a lot of times people tend to say, oh, you need eventual consistency everywhere if you're going to do event sourcing, or, oh, we can't do event sourcing because we need ACID everywhere. And the truth always falls somewhere in the middle. When you have facts to be dealt with, then, of course, event sourcing is a very fine model for doing that. If you're using views, if you're looking at your views, you're dealing with that side, or dealing with things that don't need to be fact-based, it's fine. Or things that need to have less resilience, less fault tolerance, no problem. But when your view does not require the database to be the source of truth, CRUD, no problem. Why do I say that? Because a view is not proof. A view of data is not really proof of the validity of that data you're looking at, unless the view you're looking at is all the transactions that have happened up into some specific state or some snapshot. Otherwise, your view is simply just that, dumb data. It's only data, it's only a view, it's only opinion that was formed maybe by something else, but it doesn't have any proof. And if you have zero proof, again, you still have you may have trust issues. Sometimes you need proof and sometimes you don't. So good masters are not data-driven, they actually drive data. They're stateful, they create good relevant facts. Stateless ones are informed by the facts, and sharing opinions happens across the board. You're informed by the data, you're not driven by the data. You don't let the data send you in the wrong direction. You have the intelligence, you have the knowledge, you have the logic built into you to manage. And so how do we actually manage that data, some of the things that we should do for that data? Data should be isolated. Isolation, yes, it's bad for us, but it is good for data. And that isolation should exist between both the views and the events and facts, opinions, all inside of an internal entity, an internal agent, but that isolation should also exist between certain services. You should have isolated data between certain services or between agents that have different types of promises to keep. And this is okay. Sometimes you have, for example, you may have two different services listening to the same facts and come up with two totally different opinions. And most likely that opinion may be something orthogonal, but they can come up with two different opinions based on the same facts because you've isolated that. So you want to promote isolation and autonomy by making sure that you separate the two things. So you have state-changing requests that result in facts, or you have data view requests that come from the views. So we have direction 1 and direction 2. And when you separate like this, you have no arbitrary forcing of homogeneous views. Remember, you can have two different views, you can have two different ways of articulating those views, aka two different types of databases or two different ways to store the data. You can allow the freedom to articulate them however they're needed. So enter Lagom. And Lagom is a framework that Lightbend has created to allow us to do just these things. It's built with the idea that it knows, we know that these are challenges that you have in distributed systems. We know that building microservices is not as easy as we sometimes say. We say, oh, building microservices, easy button. We're going to take our monolith, we're going to decompose it, and sometimes we think it means taking a bowl of jelly beans and just separating them out into the different types of jelly beans, and it's going to be simple. And it's not. It sometimes ends up quite chaotic because monoliths grow over time, and over time they become entangled, and there are lots of things that you really have to unwind. Or sometimes you think you're going to build microservices and you're like, oh, it's greenfield, so my microservices are going to be perfect. No problem, it's greenfield. And you end up building another type of monolith that's even more confusing and difficult to handle because you've got a monolithic data structure or a monolithic data backplane in the background. You don't want to do things like that. So Lagom empowers you to have masters and stewards of your state or your stateless through isolation and autonomous services. And what it is it's actually a thin layer on top of Play Framework and Akka Framework, as well as some other architectural patterns built in, some other tools. There's an embedded Kafka, embedded Cassandra, different things needed for all the different parts and for all the different promises that you're going to keep. And so to talk about Lagom, remember we started with these different types of data. You have your agent internal data, meaning entities, and within Lagom you have something called a persistent entity. Persistent entities are what hold and manage your distributed state. This is how you can do distributed computing and do it quite simply, quite easily, quite elegantly. You also have your persisted data. So Lagom allows you to persist data as facts and events automatically in Cassandra. You can also swap it out, but one of the big ideas behind Lagom is that it has everything required for you in order to get started, and you can change those things out at, whenever you need to. So we've got persistence automatically built in, automatic event sourcing. You've also got persistence for the views. You can use CRUD, or you can use, you can actually use a regular relational database, NoSQL database, anything that you want, Elastic, in order to persist on the view side as well. So it gives you that balance, whatever you need in order to maintain. And then it allows you to deal with external service data. So Lagom also has built in a mechanism to allow you to subscribe to other services that are producing events or facts. And so by subscribing to those services, you can also maintain, again, different forms of state, different forms of views. It allows you that type of communication. So what might an entity in Lagom look like? So let's say, for example, we have an account context. And we have these persistent actors underneath this thing is using actors, ACA actors. And we have persistent actors that are holding a current balance. And that balance is going to be the state that we're holding. And we have a promise to always have the correct state based on the transactions that are coming in and out of there. So instead of in an old traditional architecture view, you may see a layer cake architecture where there's some UI, some services, some DAOs, and some database. And all of the state is down there in the database. And we have some DAOs to go down there from the services and get back the account balance and send it back up to the UI. Instead of doing that, what we have in Lagom or persistent actors or ACA persistence or any other type of framework like this is that state, that account balance is up some levels and it's held in memory. And what you have down in the levels are the events, the transactions that have happened. So over time, the facts don't change, but you can be very flexible about the views that come out of it. So Lagom encourages you to contain mutable state, as in not mutable state objects and mutable objects, but mutable state, and publish the facts. And containing mutable state within your services prevents data corruption. You can be eventually consistent, but you cannot be corrupt. In a system, each part must take sole responsibility for their state and the persistence thereof. And this means that absolute data ownership is important. So in Lagom, again, if I have an entity with some published event, some state that it needs to maintain, whenever any data travels in, any command, anything that tries to change my state, and that successfully changes my state, I store a fact. And I store that fact in my source of truth. And even if I'm a subscriber to some other system or some other events, I can again store the facts as a source of truth. And those entities are in a cluster. They're in a cluster, they're cluster safe, cluster aware, they always maintain their current view of state. And if everything goes out of memory, say your JVM stops, falls over, whatever happens, a node goes down, because of the nature of Lagom and the architecture behind it, it will come back up on another node, do an automatic replay without you writing any code to do that automatic replay, and that state appears, just like this. Your state is back. So Lagom allows you to specialize in order to have the right properties and characteristics for stewarding those events and those views. So say I have some stateful agents, again, responsible for creating, consuming facts, changing my state, maintaining my state, and then I have stateless agents. So like I said, the truth of the matter is you could have both. And in a system, a large system, you're likely to have both. And sometimes people say, oh, what about transactions? I need to have transactions across my microservices, et cetera, et cetera. And you can do transactions inside of an entity. You can have transactions inside of the boundary of your persistent entity where you're doing your logic. This does not preclude you from having transactions if you need them. And even if you have to have transactions across a number of different services that are cooperating together to do something, you can do that. And sometimes we call that a saga. But you can build out a saga pattern in Lagom as well. Lagom uses asynchronous message passing. Like I said, it's a thin layer over Akka. So if you're looking at Lagom, once you start looking at the code, you will notice that some of the semantics are similar to Akka actors. It uses distributed persistence patterns because that is definitely the hard part to do. And if you look at an architectural diagram of what a Lagom system might look like, and we call a reactive system, distributed computing system, this is what you may see. And I guess ideally I should have popped these up one at a time, but I didn't think about doing that. But you have your stateless behavior. And stateless behavior is super easy to replicate. You can replicate stateless services, stateless behavior very easily. There's nothing to it. But then you have your stateful entities that I talked about before, and that's really the hard part. And that's the part where Lagom shines. That's the part where you've got really, to me, the star of Lagom. Yes, it does all the stateless stuff. Yes, it does all the typical API, RESTful, WebSocket, blah, 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 blah. And you can find lots of things that do that. But finding something that allows you to actually properly manage state and properly distribute stateful entities is not something that a lot of frameworks are doing yet. But I do believe they will. So this is not a Lagom forever type speech. But I do feel like this is a proper architecture for maintaining both stateless data and stateful data. So you've heard reactive, and you know that, okay, reactive architectures, you may have heard of RX or Play or Akka and Spring Reactive. And when you look at those, a lot of times, you know, you think of reactive programming. And reactive programming is just about the data flows internal to your microservices. But when you have full systems, full cooperating systems, that means that you need to start thinking about things at a system level, or you need to start thinking about being reactive and holding those reactive principles across your entities, internal, and cross entities, external, across all of your services. And that system level view, again, is what you get with Lagom. That is specifically what the tool is meant to do. Like I said, it's around Play and Akka. And I do believe that other frameworks will start to build things like this. In fact, I know of one framework, Axon framework, that does something similar to this. And I believe that it will become more prolific as people start designing and better building distributed systems. So to sum it all up, we know that data can hurt your relationships if you let it. And the way you don't let it do that is by having the proper management, the proper stewards, and understanding where the data falls so that you can manage it properly. You need to be able to empower your entities to keep their promises, to make promises. And you shouldn't let the data drive you. You should be informed by the data, and you drive your own promises. or what you need to give to the systems, the services that you're cooperating with, or the external customers you're cooperating with. Distributed systems require more care. Like I said, distributing stateless systems, it's easy, but you end up with monolithic data back pains or data sources. But distributing a stateful system, a system that manages both in the proper way, is not. It requires a little more care. So finally, after hearing this, if you're interested in looking at some code and seeing sort of the progression of a system that may go from a hello world, purely stateless, into something that is fully cooperating between multiple services and holds the state and stateless and all in the proper ways, I have an exercise here, and I guess I should probably go update the README so you can know how to run the exercise, but it's basically like a small mini course. So hold out, I will update the README, but it is a small mini course that you could take and step through and see all the different pieces and parts of that. And that is the end.